SYK and consider gravity.
Okay. Well, this is a quick arrangement, at least earlier this weekend in email, because I was visiting Stanford, and although I had they were keeping me busy there for a while, but at least luckily I could come over for the afternoon and talk to people here. I know people here also have been thinking about the specific gravity. Maybe a few people have thought about the SYK model, but I don't think most people fully are aware of what it is. It's a way of, it's sort of, I think it's a pretty remarkable situation to some extent that again, we've been thinking about ADS CFT for a long time. ADS gravity has been well studied. CFTs we know a lot about, but if you actually would ask people, do you really know of an explicit model of a holographic CFT where you can do computations? Then there are very few of them. And one of the reasons for why the SYK model is interesting is because it's an actual quantum mechanical model, which I'll write down in a second, where one can start doing computations in, and then the computations are really pointing at an interpretation in terms of gravity. The nice thing about SYK model, it has an explicit Hamiltonian. It's still kind of complicated in the sense that it involves random couplings, so it's not something that one can sort of explicitly compute. But then precisely sort of in accordance with sort of more recent sort of philosophy, what we're going to do is we have this Hamiltonian. Again, it consists of the n Majorana oscillators. The order of the interaction is p. And then the idea is that this is a quantum chaotic model, and then somewhat miraculously, or maybe because of general principles, if you introduce variables that sort of are tuned to the large n limit, and in particular look at the two-point function of the fermions over time, that even though the interactions are very complicated, and we call them sort of almost all-to-all, in the sense that one given Majorana fermion, if you let time evolve, will very quickly sort of spread out its sort of state or the information about its state to all the other ones. But then if you take this particular variable and you basically do some manipulations with the path integral of that particular Hamiltonian, then in particular if you take the large n limit, but you're keeping the order of the interaction also large in a way that the ratio p squared over n is fixed, which is known as the double scaling limit, you end up with a very geometric action that turns out to look like this, where this g is basically the logarithm of that big G. Or maybe actually the other way around, in the sense that right, this G is actually that little big G, and then when you start exponentiating it, this is actually that G to the power P. That's what this thing is. So, but in any case, this gives rise to a geometric description that seems to contain elements of low-dimensional gravity. Now, I'm going to be doing something, at least thinking about this model in a way that goes against the grain, at least if we would follow sort of the lore, then this is supposed to be anti-de Sitter gravity. And in anti-de Sitter space, there's a boundary, and then the idea would be that this theory lives on the boundary of that anti-de Sitter space, and it's a fluctuating boundary, so it's usually called near ADS2. However, there are certain elements of this theory that actually point that this is not the usual boundary system. For example, this thing indeed looks like a conformal sort of like a conformal theory. So there's a corresponding bulk, that is actually known as the Liouville theory. But if you actually take the action the way it is, then the central charge of this theory is actually complex. It's not real. So that's one hint. Perhaps we should be thinking about this thing slightly differently. And there are other sort of hints that basically point to the fact that this thing might actually be better interpretable in terms of the Sitter space. And because of those hints, and because the Sitter holography is actually an important field, because again, we live in a positive space with positive cosmological constant, and certainly for our field, it's an important step to move away from just sort of the usual ADS-CFT paradigm. And indeed, if you look at the formulas that people have produced, so it turns out that, you have a question?
Yeah. Can you explain why you saying that in Leuven second size complex, it looks like P is 1 here, so P plus 1 over P is like 2?
Okay, the thing is that the free coefficient indeed is real, but this is by local field, so if you look at the metric, it's a d tau 1, d tau 2, this is a Minkowski metric.
Okay, I see.
So even though we're in Lorentzian signature, the action looks like it's a Euclidean action. And then if you actually think about it in the appropriate signature, then actually this theory is by the way, this is one of my laws of thermodynamics. If I'm giving a talk, everything breaks down. Technology doesn't work. It's either my pointer or it's the projector. Of course, in the end, if we really get annoyed, we all go into the blackboard and I'll get my chalk hat, which probably will not break. Anyway, I'll keep talking. So basically, because it's over there, I think it's not mine. So indeed, if you start thinking about sort of the center gravity, holography would work in very different ways. At least there's a correspondence which is known as the ds-CFT correspondence. Let me first go to this thing here. The center gravity, the center space, there is a boundary to the center space, it's no longer space-like. It's sort of indeed turned on its sort of side, and then the boundary is in the past and the future. And one could say, okay, well, that's where the CFT should sit, and this is what's known as the CFT. And it indeed leads to central CFTs that have complex central charge, which just makes sense because of the way things sort of evolve into the bulk in this case. However, to me, this is not satisfactory, because essentially this is not a map between a Hilbert space and a Hilbert space. The CFT that would live in the past would not have the states of the CFT in the past would not be identified with the states that you want to associate with the bulk. Another point that I should emphasize is that even in ds-CFT, what one is computing here is not, say, a correlation function. You could compute this a correlation function of the CFT, but from the point of view of the bulk, you're basically constructing a wave function. It's the wave function that you're producing. And what do you do with wave functions? When you do wave functions, you compute expectation values, and therefore you have to take an inner product between those wave functions. And the wave function that you actually produce here is a wave function that will depend on the metric, and therefore computing the inner product would actually involve coupling the theory that lives on the boundary to gravity. So basically the inner product itself involves an integral over the boundary matrix in this case. But there's another point of view which more recently we were Witten and Jeff and other people, where we're thinking about the center holography from the point of view of sort of an observer world line, where we imagine that the dual system actually lives on the world line. And it turns out that the SYK model has properties that I'll point to that indicate that indeed we can think about it as living on the world line in the center space. It does mean something quite different than ADS-CFT. In ADS-CFT, because you're living on the boundary, you can turn on gravity. If you're living in the bulk, then gravity is still fluctuating, and therefore you have to sort of think, you have to realize that the bulk system is, that your holographic system by itself in some ways is still gravitational.
Maybe it might be
We're probably
maybe that the
oscillating between the two.
seems like too long. I'm not sure what's going on.
But okay, so let me continue. There is a sort of a triality of correspondences. I showed you the SYK model. You can go to this variable which I call G, which is the bilocal variable. That thing looks like a real theory, and it actually turns out that if you think about this theory here, you can think about it as living on the boundary of actually a three-dimensional space. So that's another sort of slight surprise, perhaps, is that we're going to be thinking about the center gravity, that we start actually in 3 dimensions. We will be reducing it first then to 2 and then maybe to 1. but indeed the SYK model is going to be living on that particular world line. And indeed, as I mentioned here, it's sort of a triality, if you wish. The SYK model is dual to some effective the real CFT, which I showed in the previous slide. And I'm going to be talking about specific gravity. And indeed, this is a known correspondence between gravity and CFTs. This is also an explicit correspondence, and I'll be talking actually about this connection. Are there questions at this point? So a little bit of phenomenology, which actually is also an important hint. As I'll show you in a second, in the double-scaled SYK model, the spectrum is actually finite, meaning the energy cannot go arbitrarily high up. And that's a feature that is not a feature of ADS, because in ADS you can put arbitrarily high energy into ADS, you get arbitrarily heavy black holes. In conformal field theory, you can have arbitrarily heavy states. In de Sitter space, you cannot have arbitrarily heavy states, because indeed you have back reaction. And in 3D de Sitter space, the back reaction is simply a conical deficit. Basically, if you put an object in de Sitter space, it's not going to be a weak black hole. It's not going to be a 2-dimensional black hole. It will simply be a space in which the boundary is no longer labeled by a total 2 pi. So this, think about this as what I would call the static patch, which I should have mentioned before. This is basically, if I put =0 in the static patch metric, but because of the presence of this E in the metric, you can actually do a coordinate redefinition, rewrite this as pure de Sitter space, but then the angle phi is no longer going over 2 pi, it's going over 2 pi times a number, which is basically this number. And that tells you that there's an angle deficit. And if we identify the length of the boundary with entropy, which the holographic principle is doing, indeed there's a relationship between entropy and energy. And one of the questions is, can we reproduce this from the point of view of SYK? Or any other microscopic theory, which we still haven't done. So I'm going to present a proposal which kind of makes a rather explicit sort of link with the bulk of the Sitter space. And basically, because of this intuition that the theory lives in the bulk. And the other intuition that I should maybe have mentioned before, so I'm kind of giving you my initial motivation for thinking about this. It turns out that if you take this CFT that was on the first slide and you compute its central charge, you find that indeed it's imaginary. However, it has a real piece that looks like 13 plus an imaginary number. And therefore, it's very tempting to basically say, since I'm going to be taking an inner product between two wave functions anyway, let's go and look at the system where I have two of those CFTs, one with 13 plus an imaginary number, one with 13 minus. I get the critical dimension equals 26, and then I can integrate over metrics as if it's a critical string theory. And it turns out that there's a whole class of theories that basically have that structure. And because of basically that particular structure, I'm going to be looking indeed at an SYK model, but not a single one. But basically, you can think about it as an entangled pair, but don't buy too much of the entanglement sort of story here. At this point, I'm just going to say I'm taking two SYK models, and I'm going to impose a condition that they both must have the same energy. So this is for me a physical state condition. And think about it, if you know about string theory, then this condition is a little bit more like the condition that L naught plus L naught bar equals 1. So basically it's telling you it's the physical state condition that couples left and right numbers. Which means that any energy state in this model is basically just the product of two energy states, one on the left and one on the right. So in some sense I haven't changed the Hilbert space at all. It's still labeled by the same energy spectrum as a single SYK model. The only thing that I'm doing is that I'm writing this thing like that.
So what is
yes. Go ahead.
Yeah, you kind of implicitly imagine your theory is two copies of double scale SYK plus Gauss.
That's one way of thinking about it. It's not necessary. to introduce ghosts, but you can kind of think this in
This
as
is
a
all complete.
it's sort of, it's basically like a physical state condition. Whether it's physically two copies, it's true that in the end, in this language, it will be most easy to construct the operators that we're talking about in the double system. Although it might actually be possible if one thinks about this thing sort of more as a modular Hamiltonian, to do the construction in one single SYK model. So in principle that would be possible, but I'm going to describe it in the double system. Is that good?
Do you want me to think of the left and right as small being two static patches? Well, what does the left and right refer to?
So I'm just, it's true. If you want to feel comfortable, think about them as left and right patches. However, I'm just
tell me what you actually mean by left and right here. I just didn't
right.
get it.
I'm just labeling the two SYK models by left and right. Right now I'm just labeling them by left and right.
Analysis is involved in 2 dimensions. It's probably left and right the same.
Because later on I need pluses and minuses, I could have ones and twos. I decided that left and right would be a nice way of thinking about the two copies.
Maybe one question that maybe you'll answer a bit later is to match correlation functions on the world line for an observer in one static patch. Are you tracing out one of the SYKs or not?
No, I will need. So basically, I call them left and right. I could also call them matter gravity, because actually this condition I could call one of them clock and physical system. So think about basically, and I'm up here I have it sort of on the slide. Effectively, one of the SYK models treats it as a clock for the other SYK model. And by the way, in some sense, this is even the better construction that I'm sort of criticizing. But basically, the papers that Jeff and Edward are writing is actually sort of a more unnatural realization of the same idea. Because what they have is they have some microscopic system that has a limit space, and then they introduce a clock, and the clock has a continuous energy spectrum. And then they impose a similar condition. Whereas, of course, if I have a system that has a discrete energy spectrum, then it seems unnatural to have a clock that has more energy eigenstates than the system. So think of, if you want, you can think about it as a clock where I'm actually just taking a copy of my original system and introduce the clock. But it means that anytime I want to introduce an operator, I should impose the satisfy the zero energy constraint. So if I want to change the energy of this guy, I should do something with the energy of that guy.
I would have thought the clock should be a lot smaller than the system.
Yeah, in your case it goes bigger.
No, it isn't.
It is bigger.
In our case, both through infinity, but morally one's a smaller.
No, it's bigger. In your hyperspace, it's bigger than the microphysical system.
No.
Yeah, if I label it in terms of energy eigenstates, then the continuous spectrum is bigger than this.
There's no discrete spectrum. The spectrum, because we're doing QFT, and the spectrum of QFT
I'll take a large n limit too, but no, Edward would agree that making the clock, having the clock having a continuous spectrum is an unnatural choice. And indeed, it should have a smaller
I mean,
spectrum.
maybe Edward's wrong about it. I don't know. I can't but
personally, I would like to have the clock have to have fewer degrees of freedom than the physical system whose time I want to measure.
yeah, I agree. And ours does. Like they're both infinity, but one's bigger infinity than the other.
Can I ask
I'm happy that you're trying to discuss. I'm happy you're joining the discussion. Good.
So implicit in this, in any of these attempts to describe the zero space, then is some sort of division. I mean, presumably any clock you actually have a zero space as part of the system, but you're somehow imposing a division of your system into a clock and the rest.
Right, and in a way, the clock is going to be provide the degrees of freedom that you can think of as sitting on the other side of the horizon. So the gravitational blessing, which is indeed the condition of satisfying this constraint, will kind of create the same situation where every time I have to put an operator here, I have to do something basically identical on the other side. And indeed, basically my condition, the way I'm interpreting this condition indeed is basically that I want to preserve the geometric interpretation. But anyway, by the way, the proof is in the end in the pudding, so I'm just going to do this thing and I'm going to tell you what the consequences are. And then you can try to interpret it at the end. Because in the end, I should say that here I'm not necessarily doing things because I want them to happen. I do things because they kind of follow naturally from following at least what I think is a reasonable physical.
So should I think of this clock as a physical object in space-time or not?
You should think about the clock as basically living on the other side of the entanglement bridge.
Ah, but then how are you using that as a clock?
Yeah, I was confused about that too.
So in the end, right, so there is going to be a separate clock that may want to be keeping track of the time difference between the two sides, and I'll talk about that one in a second.
But if I'm on one side, then like what can I actually measure? It seems not terribly useful to me having a clock on the other side.
So that's right, whether or not it's on the other side or not. This comes from the question whether or not I should interpret left and right as being left and right.
Yeah.
It's just two Hilbert spaces, one of them is the clock and the other one is the physical system I'm going to be looking at. So let me just continue at this point.
Okay.
And then you can find out later where it's thinking. So as I mentioned, a very important property of double-scale SYK is that it has a finite spectrum. If you take the double-scale limit, the spectrum is continuous. If it's not literally double-scale and it's very large and finite, it still roughly looks like this. And again, this is energy. The spectrum will have a maximum and it comes back down again. So this allows me to do something, namely that I can go to a maximal entropy state. Because the maximal entropy state, either would you say, hey, it's the maximally mixed state of this system, or I can say, hey, it's some state that basically sits at the maximum of the spectral density, and temperature is defined as the variation of the entropy with respect to the energy, and the inverse temperature vanishes here. So this is sort of like the infinite entropy and infinite temperature point, or at least the maximal entropy and infinite temperature point. So that's going to be the proposal, is that when you're basically in this state, that you can either think perhaps as a macroeconomic state, but I prefer to think about it as a microeconomic state that's localized around here. That's going to be the proposed specific vacuum. The other important property is that there's effectively an angle here. I've labeled it by lambda times s, but later actually I prefer to call it theta, and it's been labeled theta in the literature, that the spectrum is actually labeled by an angle. That sounds to me, again, very de Sitter-like, because basically that's also in the Sitter space. The spectrum is measured by an angle. So this points indeed also towards representation potentially in de Sitter.
So again, just to clarify some things. So like if you really, the maximal entropy state is just maximally mixed on the full Hilbert space.
I can define my maximal entropy state if I want it. My maximal entropy state sits here in this.
But have you restricted to subspace and said there's no states allowed outside the subspace? Like I could take a mixture of that state and another state that has different energy.
That's
that would have
correct.
higher energy.
I will be studying what other states look like and have a different energy.
Okay, so they do exist.
They do
exist. If they exist, why can't I take a mixture of them and get a bigger entropy?
You can make a bigger entropy, but no one told me that I'd have to take the maximal entropy.
Okay, so it's not maximal entropy.
It's at the maximum of the entropy as a function of energy. So I have S as a function of E, and I'm going to be sitting at the energy where S has a maximum.
Okay, so it's maximal microcanonical energy.
Correct. This is exactly the words that I was using. It's the maximal microcanonical energy. And by the way, I could even make that a pure state if I want.
Okay.
And that's my equation up here. Is I'm just going to take the state that sits at the maximum point, and then the physics of that state will start looking like this in your space. Or I can take a microcanonical state. Personally, I'm a little bit nervous about doing the full state where I really occupy all these things, because I'm no longer as certain that I got to have a semi-classical interpretation of that particular state.
Are we wanting to think of this as the global de Sitter vacuum, or just the?
You mean the first one?
Either state.
Right now, my philosophy is the following. I have an SYK model.
Yeah.
I know how to solve it in double scale and limit.
Yeah.
And we're going to do something with it.
Okay.
So
okay.
The Sitter space will be an output. It will not be the input.
Okay.
Well, look, I think it's not unfair to ask a simple state like this what that means.
At the end, I'm going to show you the result in the end. And then you can give your own interpretation of what the result is.
The second one is the static patch state, where you trace out the other static patch.
Yeah, but then I'd expect one to be in a larger home space than the other. That's,
Yeah, but I'm not doing your approach of where I'm starting with the
Sure.
situation.
I just-
Opposite.
I'm just
starting
wanting to
with
know what I should have in mind as to how things work out. Like,
I'm keeping the suspense, if you wish. But anyway, so I'm first making an obvious statement that if I take a product of two operators, in what I call the left model and what I call the right model, and I integrate it over time, then the integral over time will basically ensure that this thing no longer depends explicitly on time, generated by the h left plus h right. So this physical statement, or this h left minus h right in this situation. By the way, there's a symmetry between E and minus E, so I'm not always committal about how I'm treating my signs, but anyway, doing this sign choice, and this condition is solved by that expression. And think about it as the way you would construct vertex operators. In string theory, vertex operators have to be integrated over both sheet. You take the vertex operator and you say your meta theory, if you wish, and then you make sure that you gravitationally dress it in a way that the total formal dimension is equal to 1. And that's what this operator is doing. So, and again, for me it was natural at some point to start thinking about these operators, and I should mention one thing, which I won't be able to explain in a seminar, but if you actually go into the papers where people have solved these models, and you look at the formulas, it turns out that if you take this particular combination, and you start computing the correlation functions, it turns out that those correlation functions actually match with expressions that people have already obtained in two-dimensional quantum gravity. So these things actually match as part of this triangle of developers. Which was the reason why I was sort of interested in it, but I didn't yet have an interpretation for what this thing would mean. And when you look at the formulas that people have, the formula that you actually get for that correlation function is essentially, you can write it in frequency space, you do the Fourier transform. And then the Fourier transform turns out to be a product of theta functions, basically. It's an expression like this. For the experts in Schwarzschild quantum mechanics, quantum mechanics looks exactly like this, the correlation functions, but then these are gamma functions. For experts in Liouville theory, correlation functions look exactly like this, and these are called epsilon functions. If you want to do double-scaled SYK, you get an expression that looks exactly like this, but then these are the Q-deformed ground functions. But for the thing that I just wrote down on the previous slide, these things are going to be theta functions. So this is what it looks like. This is actually an expression that you can find in a paper by Samolotnikov in Studies of Two-Dimensional Gravity. So that was one of the reasons why I was interested in this. And then for a long time I didn't know what it was. And then I thought, hey, at some point I have to do that integral, and I was scared to do the integral with that expression. Then I just say, hey, what's this thing going to be doing in the semi-classical limit when lambda gets small? So lambda basically sets the effective radius of the dual space. So I'm going to take the lambda to 0 limit and then see what it does. I still wasn't able to do it. I knew that I got some funny product of gamma functions until I came across a paper actually that Raphael wrote with Andy Strominger and Alex Maloney in early 2000s. This was the time, the cosmology constant was just discovered, at least as an experimental thing. People started thinking about what cosmology is in the Sitter space. People were confused at some point about what kind of vacuum the Sitter space had. You guys did a beautiful analysis of all of that. And you had some very nice formulas about basically Green's functions in the Sitter space. And indeed, it turns out that if you take the lambda to 0 to the limit of that expression in the theta functions that I had in the previous slide, you get this simple expression in terms of Koshers. And then it's not too hard to actually recognize that if you Fourier from this thing, you get an expression that looks like that. And one way of seeing it is if you Taylor expand this in powers of t, you get an expansion in terms of basically oscillating functions in terms of tau, and the frequencies of those, that expansion matches with the poles of this expression. So anyway, Fourier transforming that thing gives you that expression. it turns out that if you take the most sort of natural two-point function, the sitter interpretation of this object is the antipodal Green's function. What's in terms of the proper time on the wall line. So basically, you have the sitter space, you have the North Pole and the South Pole. You send the signal here, and you see what is the amplitude for getting it on the opposite side at a time tau later. You get exactly this expression, and this is again the sitter Green's function. It's not an anti-sitter. Again, to me, it was sort of a bit of a surprise that it's organized in this way, because normally, again, if I would only have had one of these expressions, by the way, this omega is sort of the difference between the entity, it's the change in the entity affected by the operator. This mu is some combination of delta there. The fact that I have a plus mu here and a minus mu there is because of my combination of delta and 1 minus delta. And indeed, the delta and 1 minus delta precisely appear naturally in any de Sitter physics, because for a given field of a certain mass, there's a corresponding delta. The dictionary is the same as in ADS-CFT. But then the quasi-normal modes that you get in the de Sitter space indeed are basically come in two towers. One tower with delta and one tower with 1 minus delta. And indeed, this expression has both these kind of quasi-normal modes in it. And then, so then a bit of the mystery is that this Green's function, which is the two-point function in the SYK model, actually in terms of the de Sitter interpretation, has this antipodal Green's function. And for that reason, actually, we basically introduced sort of a doubling of the operators, where essentially we include the operators, but also the operators that are rotated by half the thermal circle relative to the other one. Or if you wish, we start with one class of operators, and then half of them we move here, and the other half we move there. And I have sort of some interpretation in terms of this, which I don't want to sort of elaborate, in terms of the cross product construction, which also involves basically multiplying things by the e to the minus beta h. But basically, if I allow myself to transport one of these operators to the other side of the thermal circle, I get the actual physical Green's function. The Sitter space, the tau coordinate that are sitting here is the remaining time coordinate that's still part of this doubled system. And what I find personally exciting is that the tau coordinate of the physical SYK system, the time coordinate of the physical SYK system, is the proper time on a walk line in this space. So this Green's function is the Green's function as measured along the proper time between the final point and the initial point of the Green's function.
Yeah. Can you go back one slide and
Yeah.
see? A is plus minus.
Yeah, so what I mean by plus minus, and again I express it in the slides, but basically I'm shifting the operators a quarter of the thermal circle. If I do it by plus I beta over 4, I call it phi plus. If I do it with minus I beta over 4, I call it phi minus. So therefore I can have sort of
Sorry. But in a two-point function, you need one of them to be plus and one of them to be minus to get a de Sitter two-point function
Right.
on the same side. What if I want a four-point function or something? Then I need. Will I not? I feel like I'll only get certain wick contractions depending on which one.
the wick contractions. Yeah. So in the end, in the bulk, the interpretation of this is that at least that's basically coming out of the model itself. That its bulk dual interpretation involves a complex scalar field, where indeed phi plus is creating a field on one side, and phi minus is phi plus is creating it here and annihilating it there.
But these are not like complex conjugate operators in SYK. So somehow that you're saying that acting is like
they're what you would call the mirror operator from the point of view of the delta and 1 minus delta are, what are they called? Shadows. One of them is the shadow of the other.
So there's the delta and there's the 1 minus delta, but there's also, there's the plus and there's the minus.
The plus and the minus are sitting indeed on opposite sides of the thermal circle.
Yes, but then the Sitter they're on the same side, right? I thought you were saying the two-point function has to be on the same side.
So we're going to be dividing out a Z2 symmetry, which is a bit like the story of Harlow, where indeed we're going to identify anything that sits on the other side with the CRT or CPT transformation with everything that sits on this side. So basically, although the construction involves the two sides, later on we're going to be identifying things, and in the end the model only lives in one static patch. But it has a charts field, yes.
So just to go back to the idea that this comes from some natural construction operators. So the physical operator makes sense in the sense that it's a gravitational addressing, but this idea of splitting by Euclidean time and then performing as you do, does it have a natural physical interpretation? Like, is there a reason why we should expect that relatively correct one to reproduce this here?
No, let me just say this. At least I could have just stopped at this point and basically saying, okay, well, you're going to tantalize things off, which I'm fine with. Namely, that we just do the naive two-point function into this space that operates that you kind of get physical operators. I'm just saying, okay, well, the result is that I get this antipodal grid function, period. And then you can say, hey, how do we want to interpret this thing?
It's a little awesome to hear that. I mean, you're getting this formula from, pure de Sitter space with no band reaction. It would not be true if I don't.
Yeah, but that's because of the Q to 1 link. That's correct. Q meaning lambda to 0 link. So there's a coupling limiting to 0.
But in the end, the model that you are going to get out and that you're going to say will describe de Sitter space will be useful for describing de Sitter space with background.
With background, that's right.
And so this is meant to be an inductive process where you get some aspects of the model from this background solution. But then some of what comes out in the end is supposed to be more general.
Yeah, so it's true that if I start relaxing the condition that lambda should go to 0, so lambda is this parameter p squared over n, so this is like the strict large n limit, keeping p finite or keeping p smaller. If I start relaxing that and then lambda comes back to the story, I want to be able to see gravitational corrections to this whole thing. Or at least there should be, interactions that come from, and indeed it turns out that basically in the dictionary, lambda controls the radius of curvature. So anything that where G Newton becomes finite will go in corrections. And they need to be studied separately, which I'll talk about in the second final third of the talk.
Technical question. So you said in the double scale SYK you get gamma Qs. Yes. So where do you get the thetas from? Like, was that not an SYK calculation?
The gamma Qs is one way of thinking about. So you're familiar with this identity. If I take gamma x times gamma 1 minus x, I got 1 over sine of y times x.
Yeah.
If I do gamma cube of x and gamma cube 1 minus x, I get a theta function. And so I get the theta function because I took the delta and 1 minus delta. And this goes through for all the terms in the expression. So this combination of delta and 1 minus delta. And theta functions, by the way, are very nice. They're quasi, they're basically doubly periodic. And it turns out that these gamma cube functions are periodic, but only on a half plane. Meaning they're like gamma functions in one direction where there are only zeros on a half line, then they're periodic in that direction. And then by reflecting them and multiplying them, I get a periodic. Okay, so anyway, this is just a little piece of evidence. I very quickly, so how would one use this thing or how would one interpret it? I'm going to go quickly. Basically, if we think about this as two-dimensional space, which seems still the most conservative way of interpreting it, and basically what one is doing is, indeed, I was mentioning, basically you need the de Sitter space metric, but then you have a complex field phi living on that de Sitter space metric. Let me still mention this, that basically what the most likely form of the dual theory is some form of J gravity. I like the cosh here. Maybe by analytic confirmation you can also make this a cinch. But basically it's some kind of form of J gravity with a nonlinear potential over phi. It turns out that if you solve the equations of motion of this thing, we basically find that it has a de Sitter solution, provided that I interpret the metric not as the original one, but the one that has the dilaton in it. This freedom we always have in 2 dimensions to do this thing. I prefer to also think about that thing as potentially sort of a dimensional reduction from a 3-dimensional de Sitter metric. If I take the 3-dimensional de Sitter metric, where I combine the dilaton and the 2D de Sitter metric, this is actually 3D de Sitter. So you can think about this theory effectively as a dimensional reduction of 3-dimensional gravity. So this is my proposal.
Aren't these 2 incompatible interpretations?
These ones are
The 2 interpretations, they seem incompatible, right?
in the 3D. Don't take the 3D that seriously. It's like a Toulouse-Klein reduction. Is that what you're saying?
I'm just saying that if you interpret phi as the size of the internal space versus if you interpret phi as a 2D dilaton, they're 2 different things, right?
Yes, this is a very good point. The reason why they're sort of different is that if I have a dilaton, there's a certain way in which I could, or let's say this way, if I take this action, I could very naturally add another term, which is just the Riemann tensor times a constant. The Riemann scalar times a constant. So in 2 dimensions, I have that freedom basically of adding a topological term to the action. In 3 dimensions, I don't have that freedom. And to some extent, the end result of the analysis kind of indicates that we're needing this 2D setting where there is indeed this freedom, adding a multiple of the scalar curvature, and that freedom is basically shifting the entropy by a constant.
One function you quoted earlier, they were for 2 plus 1 disorder?
Yeah, so good point. So the thing is the following, is that this is the way I'm making the 3D de Sitter metric, but relating it to a 2D de Sitter metric. But
I'm not understanding how is this 3D de Sitter, because it's just like it's a cross product between a circle and a 2D de Sitter.
If I now take the matter field, whose Green's function I just found, and I want to write an action so that the Green's function matches with the matter field function. In your paper the Green's function was actually a 3D de Sitter Green's function. So what I'm going to do is I'm going to take a field in 2 dimensions, but I don't couple it to the 2-dimensional metric. I include the prefactor of the dilaton here, so that this is actually the dimensionally reduced action of a scalar field in 3 dimensions. I take the 3D free scalar field coupled to the 3D metric, I dimensionally reduce it to 2 dimensions, and that will give me a 2-dimensional action. And then in this 2-dimensional theory, the Green's function will match with the Green's function that I had on the previous.
You're doing, this is 3D Narii you're dimensionally reducing to get DS2 or something? Like was Raphael's calculation was in DS3?
It was presumably plain de Sitter.
Yeah, you guys were doing various dimensions, but you had a nice discussion about 3D de Sitter.
So then you're taking a dimensional reduction of just ordinary 3D with de Sitter, so this is like not Narii, so this is...
I think what we're confused about is that there's no circle in 3D de Sitter that you can reduce.
Yeah. In 3D de Sitter.
Yeah.
I'm doing 3D de Sitter has a circle direction. Wait. 2 plus 1 de Sitter, right? So I'm doing.
It's like it's a sphere across time, right?
It's a sphere across time, but the sphere has a coordinate vector around it. And it's true.
This is
Everything
like
has
singular
coordinate
around.
around, but it's not a circle. I mean, it's not a circle you can reduce onto with a fixed point.
It's not. It has a fixed point, and the fixed point is North Pole, and that's right. So I need correct.
And it's awful.
Yeah.
So the 2D theory...
And it's not a constant side.
Yeah.
So indeed, the 2D theory by itself doesn't seemingly have the de Sitter symmetry. That's a good point. I have something more to say about that. But if I take this thing, right now what I'm doing is I'm writing down an action in 2 dimensions whose Green's function needs reproduces the Green's function that I had on the previous slide. But it's correct that if you take this thing and you take the particular solution for phi. So your complaint is about this thing here, is that this thing has the DS2 symmetry,
Yeah.
but this thing does not.
Yeah, I guess so.
I guess I don't understand the equation at all, because there's a de Sitter 3D on the left-hand side, and there's a de Sitter 2D on the right-hand side plus something. And I just don't think that you can write de Sitter 3D in that way.
You can.
If by both of these things you mean like the full
If I take this,
genetically complete de Sitter space.
if I take the de Sitter metric, I'm not sure I have it here somewhere. We put E equals 0 in this equation. This is DS2 if I only take these two terms.
Sorry, this doesn't cover all of the Sitters. So.
Correct. No, but you can.
So you're wanting me to think of this patch?
So you just have to like end of the world brains in the 2D theory, but
2D theory there,
how
and the world brains,
in 3D.
and that's where the world line sits. That's right.
Okay.
I think the story, by the way, is for SYK, it's a little bit more subtle than that, and this is a good point that I think should be understood better. It turns out that SYK itself has an SU11 symmetry, effectively an emergent SU11 symmetry. And I think it should be possible to do the dimensional reduction in a way that preserves the SU11 symmetry. These are old slides, at least I should say. I've sort of learned more since the time that this was proposed, or at least that this. So it could well be that the actual interpretation slightly needs to be modified. And indeed, there are different ways of doing a dimensional reduction from 3D to 2D.
Can you go back to that formula that considers 3D and 2D?
The 3D metric, this one?
Yeah. So this.
In the static patch, this is a true formula.
So the origin of the static patch here is how do your coordinates work?
Yeah, I had it in the figure. UV equals -1.
So the circle, I see. So that's where the circle is 0 size.
Correct.
And then you're letting the circle grow out towards the edge of towards the ends of the intervals.
That's right.
And so your 2D metric is really just like its time goes an interval. And the ends of those intervals are the weather.
Correct. So the 2D is just the spatial direction.
Which actually, you don't want, doesn't that mean, does the interval run from the origin of the static patch to the horizon, or does it have like, it's symmetric, it runs to like... I'm trying to understand whether your circles are really circles or just half circles.
Yeah, these are good questions. In the end, as I said, since then I've thought about it slightly differently than just by purely dimensional reduction. Personally, I think what's actually happening is that sort of the 3D metric looks like this. And rather than just doing the circle reduction, what I actually should be doing is essentially there's a Z2 symmetry that one can impose on the Sitter space. That if you divide it out, it breaks the isometry of 3D de Sitter space from SL2C to SU11. And that picks out a preferred 2D slice, and that 2D slice still has the de Sitter symmetry. And then the Green's function lives on the center of the static patch of that 2D slice.
Why not just think we call something a dimensional reduction? I mean, it's only a useful concept when it's like on a circle of constant size or something like that. Right? If it's not that, then it's usually better to just think of the higher dimensional.
I kind of agree. To some extent, the higher dimensional picture is correct. For me, it's more a form of conservatism that I'm saying I'm doing the dimensional reduction because I don't want to immediately claim that the theory actually knows about angular momentum states in 3 dimensions. So if you wish, it's the 3-dimensional theory where at the moment I'm agnostic about how to make things that have non-zero angular momentum.
I mean, it's the S-wave sector.
It's the S-wave sector. Yeah, but S-wave sector and the circle reduction are kind of almost the same thing. And by the way, once you've chosen this point of view that there isn't a preferred world line where the observer lives, and if the boundary theory lives on that world line, looking at the S-wave sector is not an unnatural thing to do initially. And then you can try to ask the question if you can also go to things that have non-trivial angular momentum.
Should I be thinking of there being something physical at this world line? Like, is there energy at that world line?
Yes. So here I can get the Green's function, and here I got this Green's function, and it is focusing on this particular state that has this amount of energy, which sits at the maximum of the entropy. I could also take the state and put it at some other value of the energy.
Yeah.
And then indeed the formulas start changing. And the proposal is that the formulas change in a way where this actually means that I'm putting a conical deficit. That indeed, so the actual energy in the SYK model corresponds to energy that sits on that low line. Or at least it has the same kind of back reaction on the horizon.
So I should think of this as really DS3 with two points, two world lines cut out at either point in the antipode. Somehow microscopic degrees of freedom living there that can carry energy or negative energy. But then okay, so that picture seems fine, but then I don't understand how this operated dictionary is related. Like if we should be thinking of one of the SYKs living at each of the things, then why are our operators like
so I don't, by the way, in the case of DS holography, I don't think we can think about the two sides as just being coupled through entanglement. Something else has to be coupled. And my proposal is that I'm coupling the two sides to the zero energy condition. Or at least, maybe that's not even the right way of saying it. In the end, the dictionary is more subtle than that. I would say even the two sides is not entirely obvious because I think that the system is actually an oriented fault where you basically have folded the other thing back in only one step.
I thought you put a gravity, like imagining both is there and then complete to the center side, zero and integral over gravity in the end, in two-dimensional theory or something. In introduction you said that.
Right, yeah, so that's part of what we're doing. Okay, so let me just try to, you know what, I'm going to sort of go at lightning speed, sort of saying a few more words about things, because this is only, the story is actually much bigger than this. This is one result. I think there are 3 or 4 other results that would have been useful to talk about. There's one other thing that I want to mention, which has to do with the lambda corrections. So unless there are questions about this, I think basically the conclusion I would say is that we're computing, we identified an operator with that, which at least at some point I thought was a natural operator to look at. If we already didn't know what the Green's function would look like, it ended up being the Green's function in 3D de Sitter space. It could have been 2D de Sitter space, it could have been 3D. But it ended up being this. And then the question is, then the model should tell us what the actual interpretation of this is going to be.
And to get that, you had to take lambda to 0, where lambda is the DSSYK, like it's...
right. So basically at that point the data function becomes cinches, and then, or at least, and then you get the Green's function.
So lambda goes to 0 is the opposite limit from the usual SYK, the JT limit.
It is the
It is the JT limit.
By the way, if you do my doubling construction in the Schwarzschild quantum mechanics, you're going to get something very similar.
Okay, so
that's
all of these predictions could be understood just using JT calculations, but they would be
no. Let me make one important comment. So here's an important comment. So what people do in JT gravity is they take where's the expression? I have the expression in terms of here we go. So I wrote this thing as lambda times s, which was maybe a bad notation because it turns out that this special point where the entropy is maximum is maximal as of order where s is of order 1 over lambda. So the spectral density indeed has this form of this form. And lambda times s is this coordinate. And here I'm sitting at order 1 over lambda. So to get to the sitter, what you do is you take s to be of order 1 over lambda, and then you take lambda to 0. So in order to get n to the sitter, you take s finite, and you take lambda to 0, and then you're sitting here. So in that fact, the sitter and the n to the sitter, it's not that the two things have to be the same thing. No, they're sitting in opposite regimes.
So if you do this CRT quotient report and the antipode are the same, like you just said, then how can you be in the inflationary patch?
How can I be in the
the top right angle triangle?
No, in the end you're only going to be in the stationary patch.
But if the world is sitter, we kind of think of others as being in the concurrent patch, right?
Yeah, I'm sort of a static patch person myself.
Okay.
I believe I'm the only person in the universe that's actually doing observations. You guys are just about So I don't like being in the center of So at least in that aspect, at least if I'm only interested in observations of one observer, and then that's a good enough description. At least I would say in this case, to be honest, I was motivated in these papers by Edward, because in particular way he also had sort of this more background independent sort of point of view, where everything is done, at least he was talking about the timeline cube theorem, but basically where everything is being observed from the point of view of one timeline trajectory. And the fact that this thing came out as being the proper time on a geodesic suggests that the SYK model is living on the full one. But it's not quite as clear cut as that, because indeed it seems to know about more things. It seems to know about the antipodal point as well. And in the end, the proposal is basically that we have to do it still some kind of orbital, where this thing here is basically identified with something on that side, but then where the chart is flip side. Okay, okay, fine. It turns out that if you have something that has a temperature, because basically the Green's function looks like the Green's function has finite temperature, you can start asking, okay, well, what would an observer say about what happens to the universe around it? And then you would also start to associate differences in entropy with differences in energy. And therefore you can start talking about relative entropies, which once you know the Green's function. I probably am out of time. I could stop here. I can tell you in like 1 minute about a result that I'm kind of excited about, which is sort of on the opposite side of the story. Just looking at the partition function, but then thinking about things from all orders in lambda. And it turns out that basically if you can do 2+1 pure gravity in 2+1 dimensions is a soluble theory. You can actually compute its spectrum. If you choose a particular Hamiltonian, you can compute the spectrum of that particular Hamiltonian. And when you do that, you actually find that there's a precise correspondence with what's called the port rules that people have developed in the context of the SYK. I'm sorry, the double scale SYK, which I'm not going to do some people the SYK. But the double scale SYK, indeed, because of this double scaling limit, turns out that the Feynman diagram is organized in a very nice way, which is called ports. So it's a little bit confusing because this line here, it's a single line, but it represents P fermion propagators. But because of this order averaging in the J's, you kind of weight contract in the J's and the size of weight contract along with them. If you then sort of start acting with a number of Hamiltonians, you start generating a number of these weight contractions. And then Board rules follow from the observation that if you have an intersection between these things, that there are a certain set of minus signs that you can combinatorically count. And then there's a factor of Q that is associated with that intersection. And that Q is e to the minus of lambda. So lambda is the number that I was talking about before. And then it turns out that basically the whole spectrum of the theory, so here's actually the combinatorial computation of this lambda. Basically it's a Poisson distribution with minus signs because of the Fermi statistics. But anyway, if you then label the Hilbert space sort of in auxiliary form by means of the number of ports, you can write down a recursion relation. That means if I act with the Hamiltonian, I either add one of these lines, like this, or I take one line away, but I can choose which line I take away, and that leads to an extra prefactor, because depending on the line I'm taking away, I get this number of powers of Q. And then in this recursion relation, you basically have a geometric series of powers of Q, which is this number n, is called the Q integer. So this actually, if you think about it, it looks the way an operator X in the harmonic oscillator acts on the energy eigenstates. Because X is A dagger plus A, this is the A dagger piece, this is the A piece. It's just a slight relabeling because normally you write a square root here and a square root there, but this is basis transformation. So we have this thing that's called the Q harmonic oscillator. And I'm just going to tell you in 1 minute how the thing follows from gravity. So what you basically do is you introduce what you can call a gravitational Wilson line that goes around the equator. So if this is your rope line, at least this is again the line in which the SYK model lives, then there's going to be an observer horizon. And I can introduce an operator that measures that deficit angle. And the deficit angle, again, is an angle. It turns out that taking the trace of the angle is actually sort of the right thing to do, meaning the trace of the holonomy is called, basically you're doing a rotation. So the actual variable that I'm going to introduce is a variable that will measure the deficit angle. The deficit angle I'm going to call 2 pi alpha, and therefore my observable that will measure the deficit angle has this spectrum, where this is just the eigenspectrum of the deficit angle. And then the comparison is going to be with the SYK Hamiltonian, which has this eigenspectrum. So that, of course, suggests some kind of identification between this angle and that angle. And indeed, when theta is pi over 2, which is where the cosine is equal to 0, that's the point where I want to put alpha equals 0. Now, 2 plus 1 gravity again is soluble, and if I just basically start creating a Hilbert space by having this operator, and having an operator that sort of basically is going to measure the time difference between the north and the south point. So there's another dual gravity operator that basically compares the south and the north point in this way. Then these things will satisfy certain commutation relations that one can compute. And if you do that, in the end, okay, I could sort of tell you much more about it, but in the end, the conclusion you're going to find is that, so this is the drawing I just had a moment ago, is that these variables, which are called LA, can be expressed in terms of geodesic lengths. And the way you actually start doing things in terms of the quantum theory is that when I compute length in a gravity theory in 2 plus 1 dimensions, it's the same basically of considering a Wilson line in the Transaminase space theory. And those Wilson lines, if I take them in the 2 by 2 representation, in the spin 2 representation, they satisfy something that's called a Skene rule relation, which is basically where non-polynomials got started. Is that if you have two lines that cross like that, I can re-express it into 2 lines that no longer cross as a linear combination like that. And this Q can be computed in terms of the level of the Transaminase theory, or if you wish, in terms of the Newton constant of the gravity theory. And it turns out if you take this relation and you start computing the spectrum of the operator that measures the deficit angle, you can start re-expressing this thing as an operator that acts on a Hilbert space. By the way, this commutation relation follows basically just from the commutation relation between Transaminase gauge fields. And as I mentioned, indeed, this Q parameter is this. But then indeed, you're going to find that there's some, it's called a Skene relation again, where you just apply it to this relation where I have an operator that measures the deficit angle, which is this guy, and the operator that's basically a light particle propagated from north and south. And you work out the algebra, and you indeed find that in the gravity theory, that the Hamiltonian, if I define it as being the Wilson line that measures the deficit angle, has the same expression in terms of A plus A dagger, in terms of Q function of operators. So it means that if I now start diagonalizing this thing, and I compute the spectrum, I will find the same spectrum as in SYK, with the complete Q dependency. So that's basically the observation, and that's another piece of evidence, but that I think really points to the with the Sitter gravity, because basically you can do the exact same calculation in anti-distance space, in 3D anti-distance space. You can do this computation. You basically get the same algebraic relations, except that this Q is going to be a phase. It's no longer going to be a real number, because the cosmological constant in anti-distance space has a different sign. This Q is going to be a phase. And as a consequence, this n is no longer going to be an integer. This n is just going to be sort of a thing that measures a mass. Or at least, so basically, the fact that n is an integer, that q is real, that automatically puts you in a context that's actually the Sitter gravity n of n. And then there's a rather precise sort of match between what we call port rules and the way in which gravitational Wilson lines intersect in the two-dimensional gravity. So let me stop there. But I think I'm ready.
Is this a kind of reason why you wanted to say the dimensional reduction is 3D gravity?
No, the thing is, at this point, right, so if you, by the way, if you think about it, in terms of history, right, so when people were doing knob theory, and Witten sort of had to go through the same sort of type of logic. John Jones, by the way, when he was, SYK model, by the way, those scale SYK is a type 2-1 algebra. It satisfies all these axioms, basically, and when you study these kind of systems sort of from the algebraic point of view, which is what John Jones was doing, and then he started drawing these diagrams. And then Witten, of course, and he had overcrossings and undercrossings. But Witten, at that point, was not yet, at least people did not have a covariant theory of the null polynomial. And that was what John Simons was, because John Simons' theory could do a three-dimensional. But if I am in 3 dimension and the only thing I can do is throw some knots into, some ball points into 3 dimensions that start bonding with each other, do I really know about what angular momentum is?
Yeah.
I don't know what angular momentum is in 3-dimensional Chern-Simons theory. I would have to sort of make it emergent coming from something else. And it's true that in this case, in 3-dimensional Chern-Simons theory, these brain properties link to something that's called a quantum group. In that case, it's the SU2 quantum group. SU2 quantum groups have finite dimensional representations. It turns out that if you do this for the SLCC or for SU11, then indeed you get a different quantum group. And that quantum group basically describes the gravitational interactions between both lines. And then in the Q to 1 limit, the quantum group becomes an isometry group of some geometric space. And then perhaps you can start thinking about space-time symmetries.
So to match the Hamiltonian of double-scaled SYK with the algebra of the Hamiltonian and the other operators in double-scaled SYK with the algebra of these operators in 3D Chern-Simons, did you need to take Q to 1? Maybe I missed that.
I mean, once you include this relationship, it becomes exact for all of them. So this thing implies the Q-deformed harmonic oscillator equations, which allow you to solve for the spectrum.
The statement should be that the spectrum of double-scaled SYK exactly agrees with the spectrum of 3D Chern-Simons SL2C at level Q.
Correct. In the same way, so in JT gravity, people, including yourself, and have been looking at these type of variables, where basically you have the geodesic length that connects the two sides of a two-sided ADS2.
Mm-hmm.
And then there's a dual variable, which is the dilaton that sits at the center. So you have the dilaton at the extremal surface, and you have the geodesic length, and that gives you some algebra combined. In this case, there's this guy, there's that guy. Algebra is a little bit more complicated in this case, but effectively it means that this guy eventually can be expressed as a sum of to an A dagger and an A, where the A dagger and the A satisfy the Q-deformed harmonic oscillator algebra. And then the logic is basically, okay, well now I have to find the eigenspectrum of the operator that's A dagger plus A. If I would give that question for the harmonic oscillator, that would be quantum mechanics question people could answer in junior level quantum mechanics, because basically you take the harmonic oscillator and you want to know the ground state wave function as a function of x. And if you compute the ground state wave function of the Q-deformed harmonic oscillator as a function of x, in this case it's no longer x, it turns out to be this angle theta, and then you get the theta the other theta, you get a theta function of the angle of e to the I theta basically. But and it's basically this Q-deformed Gaussian.
maybe I missed that, but in double scale SYK, there's the operator and hat that measures the number of chords of a specific state. What is the n hat in 3D shared assignments? Because
it turns out that q to the n hat. So indeed, I was obviously going quickly. It turns out that q to the n hat is related to a thing that's called z. And actually, I'm quite enthusiastic about this relation too, because basically z, I introduced that as the thing that goes between the North and the South Pole. So z is the Wilson line that goes between the North and the South Pole. And it's true that if you want to compute the 2-point function in double scale SYK, what people do is the only thing they need to do is to take this q to the power n times delta, which is kind of like putting this Wilson line in the appropriate representation for a massive particle that goes between the North and the South Pole. And then you just compute the matrix element between the energy eigenstates. And if in the transimus theory, I would want to basically know what is the amplitude of bringing a particle from the north side to the south side between certain energy eigenstates, I would do exactly that same calculation. So indeed, this q to the n delta, this n, or the q to the n, is the Wilson line between the north and the south. So the question is, what is n itself? What is n counting? It turns out that what n is counting, it's a little bit funny. It turns out that if you look at the Skene relation, you have a thing that goes between the north and the south. This is the equator. And the Skene relation basically expresses this thing as a sum of something that goes diagonal from north to south and going around the Earth once. Basically, that's what this thing is. This one goes in the opposite direction. And n basically counts the number of times I'm acting with this operator. It's a bit of a funny definition, but n should mean something from the point of view. It's not entirely true that the chords are literally the root lines, but there's some reshuffling, but they kind of are somewhat.
So you write alias gravity as consignments. You expect to find a real level, not an imaginary level.
Correct.
Unlike the setter. So
Right.
I would think that Q in ADS Q would be like a fail. I think you also mentioned this.
Right.
But then something has always confused me that double scale SYK also has this ADS GT gravity element.
Right.
Is there a way to understand that in your language?
The only thing I can say about this is that if I take the q to one limit from the imaginary axis, yeah, the q equals one limit from going from the circle or going from this line, they meet in the same point.
Okay, so it's saying that the limit doesn't matter. It doesn't matter how you approach Q first.
Yeah, so I'm getting JT gravity here regardless.
Okay, I see.
And actually the fact that people talk about fake disks is because they want to interpret going basically up here in terms of a Q that has the wrong sign. And that's how the fake disk comes about.
I see. But the fake disk is stringy effect, which is not finitely infinite, right?
It's not stringy.
It's like it reduces scrambling.
Yeah, right. I would say we're not fully understanding that actually. And this is precisely discussions I'm having with Lenny actually.
Okay.
Whether what you think about it as stringy or homogeneous.
Okay.
Because indeed the mystery is the following, is that if you look at the back reaction and the dictionary that I proposed, the back reaction of order is of order 1 over lambda. At least lambda governs the back reaction. Whereas Lenny wants to have the back reaction governed by 1 over n.
Yeah.
And those things are different.
Okay.
We have some ideas about how to both be right. Even though we definitely started out, I disagree. At least it's not.
Let's thank Herman again.